You're constantly surrounded by this invisible ocean.
Oh, totally.
Right now, like as you're just sitting there listening, there are waves of energy just crashing over you,
Yeah.
passing through your walls, bouncing off your furniture, and even slipping right through your own body.
Yeah, it's wild to think about.
It is, and we take it completely for granted. I mean,
Yeah.
you put a little plastic rectangle at your TV, you press a button, and the channel changes.
Right.
You put a cold bowl of soup into a metal box, press start, and 2 minutes later it's boiling.
Exactly.
Or you step outside and you instantly feel the warmth of a star that is literally millions of miles away.
Millions of miles.
So welcome to today's deep dive. We've got this really fascinating deck of educational material in front of us, and our mission today is to basically give you a shortcut to truly understanding how all of that works.
Yeah, we're decoding the electromagnetic spectrum.
Right. And we are going to move way beyond just, memorizing vocabulary words for some science test.
Sure.
We want to discover exactly why the universe works the way it does. From that TV remote on your couch, all the way to the supermassive center of the galaxy.
And it really is a profound topic. I mean, when you hear a phrase like electromagnetic spectrum, it usually sounds like, I don't know, incredibly heavy, dense physics.
Oh, yeah. Very intimidating.
Right. It sounds intimidating, but ultimately, when you strip all the jargon away, it is just a story about energy.
Mm.
It's the story of how energy travels through the complete emptiness of space and physically interacts with the world around us.
And before anyone gets worried that this is going to feel like sitting in a high school physics class, I have to point out my absolute favorite detail from our source material right off the bat.
Oh, the cover slide.
Yes. Right there on the title page, the author just casually included a picture of the 1980s Transformer character, Soundwave.
Which is amazing.
You know, the giant blue robot that turns into a cassette player? I love that. It proves this topic is just as embedded in pop culture and sci-fi as it is in actual rigorous science.
It really is a brilliant visual anchor to start with because Soundwave the Transformer is basically a machine that manipulates energy, frequencies, and signals.
Right.
And that is exactly the concept we are unpacking today. But to understand the entire spectrum, to figure out how a microwave is somehow related to an X-ray.
Which seems crazy.
Right. To do that, we first have to establish the basic anatomy of a wave. We have to know what is actually waving.
Yeah, and the material breaks this down so beautifully into two main classifications. You have longitudinal waves and you have transverse waves.
Right.
Now, both of these involve vibrations and both of them transport energy from point A to point B. But they do it in completely different ways.
Completely different.
Like sound is a longitudinal wave, but light is a transverse wave. And the entire electromagnetic spectrum that we are discussing today, it consists entirely of transverse waves.
And that distinction is really the foundation of everything else we're going to talk about. So a longitudinal wave, like the sound of my voice right now.
Pushing through the air.
Exactly. It requires a medium to travel through. It needs air molecules or water or solid matter to literally bump into. The energy travels in the exact same direction as the vibration.
Right, so I was trying to visualize this, and I came up with an analogy to help picture the difference.
Oh, let's hear it.
So think of a longitudinal wave-like sound as a long line of dominoes standing on end.
Okay, sure.
To get the energy from the first domino to the last, they have to physically knock into each other. Boom, boom, boom.
Right.
If you take away the dominoes, the energy has nowhere to go. It just stops, which is why there is no sound in the vacuum of space. There's literally no material to knock into.
Nothing to bump against.
Exactly. But a transverse wave, an electromagnetic wave, is more like a massive stadium wave done by a huge crowd at a sports game.
Oh, I like that.
Yeah. The energy is moving horizontally around the stadium, passing from section to section, but the people themselves, they're just vibrating up and down, perpendicular to the actual movement of the wave.
See, I like the stadium wave visual for the shape of the wave itself, but here's where it completely breaks down when we talk about space.
Oh, really? How?
Well, a stadium wave still needs people, right? It needs physical matter. What's fascinating here is that the transverse waves in the electromagnetic spectrum do not need any people or air or dominoes to travel.
Wait.
Yeah, they can travel through a complete and total vacuum. They are entirely self-propagating.
Okay, let's unpack this, because that breaks my brain a little bit.
It's hard to grasp at first.
If there is literally nothing in a vacuum, no air, no molecules, no dominoes, what is actually waving? How does the energy move if there's nothing there to carry it?
You're hitting on the absolute core mechanism of electromagnetism. It comes down to two forces sort of dancing with each other.
Okay.
A changing electric field generates a magnetic field, and in turn, a changing magnetic field generates an electric field. So as the wave moves, the electric field shifts, which creates a magnetic field right in front of it.
Oh, wow.
And then that magnetic field shifts, creating a new electric field right in front of that. It is literally pulling itself forward through nothingness.
That is...
Think of it like climbing a ladder that you are building in midair, rung by rung, at incomprehensible speed.
That is a wild image. A ladder building itself in midair.
Yeah.
And because they are traveling through a vacuum with absolutely no physical matter to bump into or slow them down,
Yeah.
every single wave on this spectrum travels at the exact same universal speed limit.
Yep.
Which is just an absolutely astonishing number, 300 million meters per second, the speed of light.
And that constant speed, it dictates everything else about how these waves behave because the speed of light never, ever changes.
Right. It's a universal constant.
Exactly. Which creates a strict inverse relationship between two other properties, wavelength and frequency.
Okay, so define those for us.
Sure. Wavelength is simply the physical distance from the peak of one wave to the peak of the next.
Like measuring from one crest of the stadium wave to the next?
Yes. And frequency is how many of those peaks pass a given point in one single second, which we measure in hertz.
So if the speed is permanently locked at 300 million meters per second, you can't change how fast the wave gets to you.
Right.
You can only change the shape of the waves itself.
That's the key. If you stretch a wave out so it has a very, very long wavelength, fewer of those waves are going to pass by you in a single second.
Because they're physically so big.
Right, so its frequency drops. But if you squish that wave together, compressing the distance between the peaks, suddenly an enormous number of those waves are hitting you every single second.
And the frequency skyrockets.
Exactly. And that single mathematical relationship, stretching versus squishing, is the main difference between a wave that harmlessly passes right through a solid brick building and a wave that possesses enough raw energy to violently rip apart human DNA.
Well, that sets up a perfect transition, because I really want to look at how squishing that wave changes reality for us.
Let's do it.
Let's start at the long and lazy end of the spectrum, where the waves are heavily stretched out. These are the gentle giants.
The radio waves.
Yeah. If we look at the extreme end of the spectrum, the absolute longest waves are radio waves. And when we say long, we mean massive.
Truly massive.
The wavelength here ranges from 1 meter long, which is, about the size of a human, all the way up to 100,000 meters long.
Yeah.
We're talking about waves the size of literal skyscrapers just washing over us constantly.
And because they're so incredibly long, their frequency is relatively low.
Right.
The frequency ranges from roughly 30,000 hertz up to 3 billion hertz. Now, I know that sounds like a big number.
3 billion sounds huge.
It does, but on the cosmic scale of the spectrum, it is extremely low energy. We harness these massive waves for telecommunications, for broadcasting television signals, for the radio in your car.
But how do we actually catch a wave the size of a skyscraper? I mean, I can't see it. I can't feel it. How does my car radio turn a 100,000-meter invisible wave into, like, pop music?
It all goes back to those electric and magnetic fields we talked about earlier. We build massive metal towers and antennas to catch these giant ripples.
Okay.
When that giant radio wave washes over the metal antenna on your car, the wave's electric field physically pushes the electrons inside the metal up and down.
Oh, it actually moves them.
Yeah, the electrons dance to the exact frequency of the wave. Your car's radio receiver feels that specific electronic dance and translates it into sound through your speakers.
That is so cool.
And the best part is, because they are so large and low energy, they pose absolutely zero danger to our biology. They sweep right through our bodies without our cells even noticing.
But then we start to squish the wave just a little bit.
Yeah.
We move from the size of a building down to the size of a human, and then we cross into the next category. Microwaves. Now the wavelength shrinks. We are looking at waves ranging from 1 meter down to 0.001 meters.
So getting pretty small.
Yeah, we're talking about a wave the size of a honeybee, or even down to a tiny pinpoint. As the wave gets smaller, the frequency jumps up, now reaching into the trillions of hertz. We use these for radar, for cellular telecommunications, and of course,
cooking food in microwave ovens.
Exactly.
And this is where the physical interaction with matter really begins to shift because the frequency has increased, the energy has increased.
So they aren't harmless anymore.
No, the dangers are no longer non-existent. The data notes that microwaves can produce burns and cataracts, and the mechanism here is just fascinating.
How does it work?
Microwaves happen to be the exact right physical size and frequency to interact with water molecules.
Okay.
Water is a polar molecule. It has a positive end and a negative end, kind of shaped like Mickey Mouse.
Right, with the two little hydrogen ears.
Exactly. When a microwave hits it, the wave's electric field flips back and forth rapidly. The water molecule tries to align with that flicking field, causing it to spin and vibrate violently.
And all that violent vibrating creates friction.
Exactly right. That friction creates heat. That is precisely how your microwave oven heats up a bowl of soup from the inside out.
Wow.
And it's also why exposing human tissue, which is, mostly water to high-intensity microwaves, would cause severe thermal burns or damage the fluid-filled lenses of your eyes, which leads to cataracts.
Okay, let's unpack this, because I need to stop you right here. I'm looking at this section in the sources on microwaves, and the author put a giant question mark right next to the word cancer under the list of dangers.
Yes, they did.
That feels like a very weird thing to hedge on, especially when right above it, burns and cataracts are listed as guaranteed biological facts. Why the sudden uncertainty there?
It's a vital distinction, and it really highlights a crucial piece of scientific critical thinking. The author is being incredibly precise with the mechanical data. As we just discussed, the thermal damage, the burning, is a confirmed mechanical effect of how microwaves flip water molecules. It is undisputed.
Right, that's just physics.
However, cancer is not caused by friction or heating. Cancer is caused by cellular mutation, by actual structural damage to the fundamental bonds of your DNA.
Oh, I see.
What that question mark signifies is that while there is constant public anxiety about whether the microwaves from our cell phones or Wi-Fi routers might cause cancer over a lifetime of exposure, there is currently no confirmed definitive mechanism proving that these specific waves have enough energy to break DNA bonds.
Okay, so it's a size issue.
Exactly. The energy is just starting to ramp up as the waves shrink, but it hasn't quite reached that catastrophic threshold yet.
That makes perfect sense. It's a theoretical concern for long-term exposure, but not a proven mechanical reality like the thermal burn.
Exactly.
And speaking of burns, if we squish the wave even further, we get into infrared. Now we are looking at waves the size of protozoans, microscopic organisms. The wavelength is 740 nanometers, up to 0.01 meters.
Tiny.
We use this for heating elements, like the glowing coils in a toaster. We use it for TV remotes, and we use it for thermal night vision, like warm bodies physically emit infrared radiation.
Right.
And the danger here is very straightforward. It can burn you. If you touch the glowing coil of a space heater, you are experiencing intense infrared radiation transferring heat right into your skin.
So we are steadily marching toward higher and higher energy. And as we continue to compress these waves from the size of protozoans down to the size of individual molecules, we suddenly cross into a tiny, highly specific band of the spectrum. It is incredibly narrow. The wavelength goes from just 740 nanometers down to 370 nanometers. The frequency jumps to roughly 400 trillion to 800 trillion hertz.
Wow.
And this tiny sliver is the only part of the entire electromagnetic spectrum that human beings can actually perceive without technology. This is visible light.
The colors of the rainbow.
Yes.
740 nanometers is red light, and as you squish it down to 370 nanometers, it transitions through orange, yellow, green, blue, and finally violet.
Right.
The only danger listed here is eye damage from exceptionally bright lights like staring directly into the sun. But I have to admit, I always assumed visible light was just the, default radiation of the universe.
Oh, sure.
I thought it was just normal light, and everything else on this spectrum was some exotic, invisible radiation. But looking at this material made me realize something really profound about our evolution.
Oh, how so?
Well, there's this one detail in the slides that states visible light is the absolute best at penetrating Earth's atmosphere.
It is.
So what does this all mean for you and me? The universe is flooded with every type of wave, massive radio waves, deadly gamma rays. But it's not a coincidence that our eyes only see this one incredibly specific, microscopic sliver of energy.
Oh, I see where you're going with this.
Right. Our biology evolved over millions of years on a planet covered in a thick atmosphere of nitrogen and oxygen. That atmospheric gas blocks out a huge portion of the wider spectrum.
Thankfully.
Yes. So the energy that actually successfully pierces through the gases of our sky and reaches the ground mostly falls in this exact narrow band. We literally evolved biological antennas, our eyes, that are perfectly tuned to the specific frequency of energy that was actually available to us on the surface.
If we connect this to the bigger picture, the solar energy distribution chart in our sources proves exactly what you're saying.
Yeah?
It measures the intensity of the light coming directly from our sun. And if you look at the peak of that graph, the absolute maximum output of solar energy aligns perfectly with the visible light window, particularly right around the yellow and green wavelengths.
That is amazing.
It is a breathtaking example of biology syncing perfectly with solar physics. The star provides a specific frequency, the atmosphere filters it, and life on Earth adapted to catch whatever made it through.
It's so beautiful to think about it that way.
Yeah.
But the spectrum doesn't care about our biology.
No, it doesn't.
It doesn't stop just because our eyes stop being able to see it. So we know the visible light window is safe.
Yeah.
But what happens when the wave gets even more squished?
It gets dangerous.
Yeah, as we move past violet light, we cross a terrifying and powerful threshold.
Okay.
We enter ultraviolet or UV light.
Right.
The wavelength shrinks from 370 nanometers down to 10 to the power of -9 meters. We use it in tanning salons, in disco black lights, and security to check for the glowing threads in counterfeit $20 bills.
And we also see another incredible biological adaptation here just outside our human window.
Really?
Yeah. While our eyes cannot process UV light, bees actually see in the ultraviolet spectrum to help them find pollen.
Oh, wow.
A flower that looks plain white to you or me might have vibrant, glowing UV patterns pointing right to the nectar. It acts like a neon landing strip for the bee.
That is amazing. Nature just utilizing a completely different frequency channel.
Exactly.
But we have to talk about the danger here. We finally hit it. Skin cancer. And no question marks this time.
No question marks. And to understand why, we have to introduce the grand rule of the electromagnetic spectrum.
Okay.
As frequency increases and wavelength gets smaller, the waves eventually become so tiny and vibrate so violently that they can interact directly with the internal structure of atoms. This is called ionizing radiation. Non-ionizing waves, which include everything from those giant radio waves up to the visible light we see, they either bounce off you, pass right through you, or just gently warm your molecules.
Like the microwave.
Right. But ionizing waves, which start at ultraviolet and go smaller, have so much raw energy and are physically so small they act like molecular wrecking balls.
Wrecking ball.
Literally.
Yeah.
They can actually knock electrons entirely out of their orbits and shatter the chemical bonds holding your DNA together. That shattered DNA leads to mutations, which leads to cancer.
That wrecking ball visual is terrifying. But it perfectly explains an everyday action. Like when you smear SPF 50 sunscreen on your face at the beach, you aren't just putting on cosmetic lotion.
No, not at all.
You are literally wearing liquid body armor. You are creating a chemical shield to stop microscopic high-frequency bullets raining down from the sun before they can shatter your DNA.
That's exactly what's happening.
But what happens when the wave gets so incredibly microscopic that it doesn't just hit your skin, it slips right through your flesh entirely?
Then you have crossed into X-rays. Wavelengths from 10 to the -7 down to 10 to the -12 meters.
Incredibly small.
We use them for security scanners at the airport and obviously medical imagery. The danger, again, is cancer because they are highly ionizing.
Right.
There is a really haunting historical image in the source material that illustrates this perfectly. It's a grainy black and white photo of Wilhelm Röntgen's first medical X-ray.
Oh, I know this one.
It's an image of his wife's hand. You can clearly see the dark silhouettes of the bones in her fingers and a massive, opaque, black lump on her ring finger, which is her metal wedding ring.
I've seen that picture. It looks like a ghost.
It really does, and it revolutionized medicine overnight. Röntgen discovered that because these waves are so incredibly small and high energy, they pass right through soft tissue like skin and muscle without hitting anything.
You just slip right through the atom.
Yeah, but they get blocked by dense materials like bone or heavy metals. Suddenly, you could look inside a living human body without cutting it open.
Which is a miracle.
It is. But the danger of ionizing radiation wasn't fully understood yet. Exposing tissue to X-rays is literally shooting those molecular wrecking balls deep into the body.
Oh, man.
It's why today, the dental hygienist puts that heavy lead apron over your chest before taking an X-ray of your teeth. The lead is dense enough to absorb the wave, protecting our vital organs from the ionizing energy.
And then we reach the absolute extreme end of the spectrum.
Mm.
The smallest, most energetic, most violent waves in the universe.
Gamma rays.
Gamma rays. We are talking about wavelengths the size of atomic nuclei, 10 to the negative 16 meters.
Unbelievably small.
And the frequency is a staggering 3 times 10 to the power of 24 hertz. The number of vibrations happening every single second is almost incomprehensible.
It is.
We use these for observing the most extreme events in the universe, like supernovas. And the danger is, unequivocally, cancer.
Yes.
But here's where it gets really interesting. There's a massive paradox here. Gamma rays are listed as a cause of cancer, but right next to it, under uses, it lists them as a treatment for cancer.
Mm.
How can the ultimate molecular wrecking ball be used as a medicine?
It is a brilliant paradox, and it perfectly illustrates how human engineering has learned to harness the physics of this spectrum.
Okay.
You described gamma rays earlier as being so small and energetic they destroy DNA. If a stray gamma ray hits a healthy cell, it will mutate the DNA, potentially causing a healthy cell to become cancerous.
Right. That is why nuclear fallout is so deadly.
But consider the inverse. What if you already have a tumor? What if you have a cluster of rogue cells that you desperately want to destroy?
Oh, you use the wrecking ball on purpose.
Precisely.
Yeah.
In modern oncology, doctors can use specialized machines to aim incredibly precise, intersecting beams of gamma rays entirely at the cancerous tumor.
Wow.
Because the waves are so small, they act like microscopic atomic scalpels. They deliver a lethal dose of ionizing energy exactly where it is needed, intentionally obliterating the DNA of the cancer cells so they can no longer reproduce.
That is wild.
And by carefully angling the beams, they leave the surrounding healthy tissue relatively untouched. We are literally taking the deadliness of the wave and weaponizing it to kill the disease.
That is just incredible. We take the very thing that destroys our biology and we use it to save ourselves.
Yeah.
It really brings this entire journey full circle. I mean, we've gone from massive waves the size of skyscrapers washing over our antennas to broadcast the morning news, down to waves the size of a honeybee physically spinning water molecules to cook our dinner. We've looked at the tiny sliver of visible rainbow that our eyes evolved to catch, past the glowing UV landing strips for bees, and finally down to the atomic wrecking balls of X-rays and gamma rays mapping our bones and fighting tumors.
And the most important takeaway for you, the listener, is to remember that every single one of those things we just listed is the exact same underlying phenomenon.
It's all the same thing.
From the 100,000-meter radio wave to the microscopic gamma ray, they are all just transverse waves of energy. They are all electric and magnetic fields pulling themselves through the vacuum of space at exactly 300 million meters per second.
Yeah.
They are just wearing different masks based entirely on how stretched or squished they are.
It completely changes how you look at the physical world. Which brings us to the final thought we want to leave you with today.
Yeah, this is a good one.
The very last piece of our source material is a map of the entire galaxy. It's plotted with things like pulsars and massive solar flares and unidentified galactic energy sources, and it makes you realize something truly profound. If human eyes only evolved to see the tiny specific window of visible light that manages to penetrate our atmosphere, imagine what the night sky would actually look like if your eyes could process the entire electromagnetic spectrum at once.
It's a staggering thought experiment. If your vision wasn't limited by our evolutionary biology, the night sky wouldn't be a dark, empty void with a few white pinpricks of starlight.
No.
It would be a blazing, blinding kaleidoscope of energy. You would look up and physically see the massive, sweeping radio waves washing over the planet.
It's just rolling over us.
You would see the faint microwave background radiation left over from the birth of the universe itself glowing in every direction.
Oh.
You would see the violent, invisible bursts of gamma radiation erupting from dying stars in distant galaxies. You would realize that what we consider to be the real world that we see every day is actually just a tiny, tiny fraction of the energy that is constantly dancing around us.
You are sitting in the middle of a cosmic light show right now, and you can only see a sliver of it. We want to thank you for joining us on this deep dive. We hope that the next time you pick up your TV remote, or stand in front of your microwave, or just look up at the night sky, you see the invisible waves moving all around you. Keep questioning, keep learning, and we'll catch you on the next deep dive.
So, I want you to picture stepping into a 2010 middle school classroom.
Oh man, the nostalgia.
Right. You're expecting a basic, maybe slightly tedious science review.
Yeah, you definitely know the drill.
Exactly. Just, memorizing vocabulary and filling in blanks on some worksheet.
The classic routine.
But instead, hidden inside this seemingly mundane slide deck, you find the fundamental fabric of reality just laid bare.
It really is a striking juxtaposition. I mean, we are looking at a very specific set of educational materials today.
Yeah, it's a presentation titled Part 4, Lesson 4, Intro EM Spectrum
Created by an educator named Ryan P. Murphy in 2010.
from sciencepowerpoint.com, right?
Exactly. And on the surface, it's just a standard work bundle. It's got these red slides that signal to the students, hey, pay attention, this part is on the test.
Yeah, the literal red flags for learning.
Right.
And I want you, the person listening right now, to really put yourself in that classroom. Because the very first slide you see doesn't hit you with Maxwell's equation.
Or the speed of light or anything like that.
No, it hits you with literal classroom rules.
Which is so funny to read as an adult.
It says in big letters, make good choices.
A solid life rule,
It's
honestly.
And then it reminds you, please, no shout-outs.
One speaker at a time. Please raise your hand.
Yeah, and it demands first, last, and always focus on task completion.
Which, from a purely pedagogical standpoint is entirely necessary when you're trying to corral a room full of energetic middle schoolers.
Oh, for sure. You need baseline order before you can even attempt to introduce abstract physics.
You absolutely do.
But I'd actually take it a step further, I think.
How so?
Well, when I was looking over these rules like avoid distractions, stay organized, help others, and never give up, I realized something.
Was that?
They function as a surprisingly robust epistemological framework for doing actual science.
Oh, wow. Okay, I see where you're going with this.
Right. Like, I'm assuming the author didn't necessarily intend for Make Good Choices to be a philosophical treatise on the scientific method.
Probably not.
But to understand the invisible electromagnetic spectrum, you genuinely have to follow those exact tenets.
That's actually a really fascinating way to read it.
Yeah.
Yeah, because to grasp the mechanics of invisible fields, you do have to literally avoid distractions.
Right.
Meaning, you must look past the macroscopic, tangible world. Your primate brain is biologically wired to prioritize.
Because it's invisible.
Exactly.
Yeah.
And you have to stay organized because the mathematics of frequency and wavelength build upon each other so systematically.
They really do.
And, maybe most importantly, you absolutely must never give up.
Because it's hard to wrap your head around?
It inherently defies everyday human intuition. You are being asked to visualize phenomena that are, by definition, completely imperceptible to your eyes.
So if we treat these classroom rules as our sort of mental prep for this deep dive, we can finally jump into the unseen world.
Let's do it.
But the slide deck doesn't actually start with light waves at all.
No, it takes a really interesting detour first.
Before we even touch the electromagnetic spectrum, the author establishes this grand overarching premise about how the universe operates.
And the core message there is that the universe is not a static diorama.
Right. It is an engine of continuous, relentless transformation.
Which is a crucial grounding mechanism for any informed mind.
Okay, let's unpack this a bit.
Well, before you can categorize the different types of energy, you have to establish the first law of thermodynamics.
That energy cannot be created or destroyed, only altered in form.
Exactly.
And the slides explicitly state that. They say energy can be transformed from one form to another.
And to illustrate this, the source material uses two completely disparate visual examples, which I loved.
Yeah, the first one is a photograph of a classic wooden Yamaha grand piano sitting in a living room.
Just a totally normal piano.
And right next to that, we have a highly detailed diagram of the rock cycle.
The contrast is pretty stark.
It explicitly notes how the rock cycle is driven by plate tectonics, complete with these images of grinding crusts, deep canyons, towering mountains, and molten magma.
At first glance, coupling a piano with plate tectonics in a lesson about light feels like, well, a disjointed leap.
It really does. Why start a presentation on light waves with a piano and the rock cycle?
But analytically, it does exactly what it needs to do.
Yeah. My read on this is that the author is framing the universe as the ultimate, inescapable recycling plant.
That's a great analogy.
Nothing is ever truly lost,
Right.
Whether you are looking at the massive slow-motion violence of tectonic plates crushing ancient mountains into magma,
Which is incredible to visualize.
or you are just looking at a Yamaha piano. It's all just energy wearing a different mask.
Let's break down that piano example, actually.
Yeah.
With the piano, you have the kinetic mechanical energy of a human finger striking a key.
Yeah.
That force physically causes a hammer to strike a metal string.
Right, mechanical transfer.
And then the string vibrates, transferring that mechanical energy into the surrounding air molecules.
Creating alternating waves of high and low pressure.
Exactly, which we perceive as an acoustic sound wave.
And then with the rock cycle, you basically have a macro scale version of that exact same kinetic transfer.
Precisely. The gravitational and thermal currents in the Earth's mantle physically drag massive continental plates around.
And when they collide at a subduction zone,
The immense mechanical friction is converted directly into thermal energy.
just melting solid rock into magma.
The educator is demonstrating scale here. Energy transformation happens when you press a piano key, and it happens when continents collide.
Which primes the brain perfectly, I think.
If we connect this to the bigger picture, it makes total sense.
Because if you just jump straight to, hey, here is an invisible gamma ray traveling through space.
It just feels like science fiction.
Exactly. But by grounding the lesson in the piano and the mountains first, the student, and you listening right now, internalizes a core truth.
That a light wave isn't some magical, ethereal ghost.
No, it is simply another manifestation of this exact same universal recycling process.
We are establishing the baseline reality that the stage is constantly moving.
So once you accept that energy is in a state of perpetual transformation, the natural next question is, well, how does it physically relocate?
Right? How does energy actually get from the vibrating piano string to your eardrum?
Or from the sun to the earth?
And this transitions the material to its specific area of focus, waves.
The source materials draw a very hard line here. They divide waves into two distinct categories,
You have mechanical waves on one side.
and light or electromagnetic waves on the other.
But before detailing the differences, the slides are incredibly careful to define both strictly as energy waves.
Why is that phrasing so important?
It's intentional and vital because a very common misconception is that waves are made of physical matter moving forward.
Like the water itself is traveling across the ocean.
Exactly, but they aren't. Waves are a disturbance, a pulse of energy moving through matter or space. The material itself largely stays in place, just bobbing up and down, while the actual energy travels horizontally.
That makes sense. And the slides illustrate that first category, the mechanical wave, with a crisp, high-resolution photograph of cresting ocean waves.
You can see the massive swell of water, the white foam breaking at the peak.
And the text explicitly notes that a mechanical wave travels through a medium.
Because a mechanical wave fundamentally requires a physical substrate to exist.
It needs atoms to bump into other atoms.
Precisely. Without the water molecules in the ocean or the air molecules in the room,
Or the dense atomic structure of the ground during an earthquake.
a mechanical wave simply cannot exist. It requires a physical vehicle.
But then the presentation introduces the electromagnetic wave.
And this is where the paradigm shifts.
The slide notes that EM waves can travel through a medium like sunlight, passing through the glass of a window, or refracting through water.
But it introduces a profound new capability.
It states that EM waves travels through vacuum of space.
And the visual shifts drastically here.
Yeah, from the earthly ocean to a sprawling, glowing spiral galaxy.
And another image of our blazing sun.
The text lays down the ultimate rule, saying, an electromagnetic wave transports its energy through a vacuum at the speed of light.
The concept of a wave traveling through a true vacuum is where everyday human intuition completely breaks down.
I want to really chew on this for a second because here's where it gets really interesting.
Okay, lay it on me.
Imagine the sheer emptiness of interstellar space.
Nothing but void.
Right. There is no air, there is no water, there is a terrifying lack of physical particles.
It's a true vacuum.
So if a mechanical wave is like a line of people passing a heavy bucket of water down the line,
Where the people are the medium required to move the energy.
exactly, then an EM wave is like someone throwing the bucket directly across a bottomless, completely empty chasm.
That's a great way to picture it.
But how is it physically possible to have a wave of nothing?
It sounds like a paradox.
It does. How does a ripple propagate when there is no pond to ripple in?
Well, the slides actually provide the answer visually. And what's fascinating here is that it requires us to look at the geometry of the wave itself.
Okay.
The diagram provided shows an electromagnetic wave not as a single undulating line, but as a dual-axis structure.
A dual-axis structure.
Yeah, you have a red wave labeled electric field oscillating vertically, up and down.
Okay, I can picture that.
And simultaneously, you have a blue wave labeled magnetic field oscillating horizontally,
Right.
side to side.
So they are locked perfectly perpendicular to each other, moving forward together.
Exactly.
It kind of looks like a braided rope or a three-dimensional double helix.
That's a very accurate visual.
But how does that solve the chasm problem? If there are no atoms in the vacuum, what is actually waving?
The fields themselves are what is waving.
Wait, really? The fields themselves?
Yes. This is rooted in the principles synthesized by James Clerk Maxwell back in the 19th century.
Okay.
A changing electric field doesn't just sit there. Its variation mathematically induces a magnetic field. And conversely, a changing magnetic field induces an electric field.
So they're essentially leapfrogging each other through the emptiness.
Well, leapfrogging implies they take turns, which is a slight oversimplification.
Oh, okay.
It's more of a continuous, simultaneous regeneration.
Got it.
As the electric field oscillates and decays, it generates the magnetic field, which in turn generates the electric field as it decays.
The wave acts as its own medium.
Yes, it pulls itself forward by its own bootstraps, so to speak.
It is wild.
It doesn't need a physical substrate because the interaction of the two fields provides the necessary structure for the energy to propagate.
That is deeply counterintuitive, but entirely elegant.
It really is.
It literally paves its own road as it drives at 299,792 kilometers per second.
The speed of light.
And this explains a very specific, almost bizarre section of the student worksheet included in the source material.
You mean the section asking the student to draw their understanding of electricity and magnetism?
Yes. I was so confused at first. You're flipping through slides about space and galaxies, and suddenly the worksheet demands, describe your understanding of electricity.
And it provides a space next to a drawing of a human brain, a jagged lightning bolt, and a classical atom model.
Right. And right beside that, it demands, complete a drawing of the invisible magnetic field based on the bar magnet below.
It seems like a jarring detour back to third-grade science.
It really does, but it's actually an incredibly sophisticated pedagogical move.
Oh, absolutely. The author is forcing the student to unify these concepts manually.
You cannot understand how a galaxy's light reaches your eye unless you first accept the electricity firing in the neurons of that drawn brain.
And the static charge of the lightning bolt.
And the pull of the bar magnet on your refrigerator.
They're not separate phenomena.
They're two faces of the exact same fundamental force.
Exactly. When a charged particle moves, whether it's an electron in a radio antenna or plasma in a distant star, it disturbs that unified electromagnetic field.
And boom, you have your self-propagating wave.
Precisely. The educator is grounding the abstract speed of light in a vacuum in the tangible reality of a bar magnet.
That is brilliant teaching.
It really is. And once we understand this unified force and the mechanism of its self-propagation, the curriculum must move to categorization.
Right, because how do we differentiate one electromagnetic wave from another if they are all made of the exact same oscillating fields?
And all travel at the exact same speed in a vacuum.
Which brings us to the core mechanism of the lesson, decoding the electromagnetic spectrum.
The slide defines it cleanly, the entire frequency range of electromagnetic waves.
And it provides the classic wide format chart mapping out the categories from left to right.
We all remember this chart.
Oh, yeah. Radio, microwave, infrared, visible, ultraviolet, X-ray, and gamma ray.
The labels are standard, but the crucial information is in the mathematical relationship illustrated on the axes of that chart.
Okay, break that down for me.
Well, we have wavelength on the top, measured in meters,
Right.
and frequency on the bottom, measured in hertz.
And the slides place massive emphasis on the inverse relationship between the two.
They really do. On the far left, the radio wave end, the text aggressively points out that this area is low frequency.
And it pairs it with large wavelengths.
Exactly. But as you slide your finger across the chart to the far right, the gamma ray end, it completely flips.
Now you have high frequency paired directly with small wavelengths.
It is an inescapable mathematical reality.
Because the speed of the wave is constant, right? The speed of light.
Right. So if you increase the number of waves that pass a point in a given second, which is the frequency, those waves must physically be shorter.
They have to be packed closer together to maintain that constant speed.
Exactly.
I really want you to visualize the graphic they use for this because it's so clear. They draw a continuous black line across the chart.
It starts on the left.
Yeah, in the radio section, the line forms these wide, lazy, rolling hills. The distance between the peaks is massive.
But as your eye tracks to the right, those rolling hills start compressing.
Rapidly. By the time you hit the visible light band right in the middle, they are tight, rapid zigzags.
And when you arrive at gamma rays, on the far right.
The line is just a frantic, solid block of hyper-compressed scribbles.
The student worksheet then requires the user to actually fill in a spectrum box from large to small.
And they have to provide one example of how each wave is utilized on Earth.
This is where the physics leaves the chalkboard and really collides with engineering and biology.
Okay, let me test a hypothesis here about why the author did that.
Go for it.
The reason the worksheet demands real-world examples is to prove that this chart isn't just an arbitrary taxonomy.
Right.
The actual physical size of the wavelength, whether it's a lazy rolling hill or a frantic scribble, entirely dictates how that invisible wave interacts with objects in the physical world, right?
That is the fundamental takeaway. The dimensions of the wave determine its physical behavior when it encounters an obstacle.
So if we look at the extreme left of the chart radio waves, those wavelengths can be meters or even kilometers wide from peak to peak. Because they are so physically massive, they interact with the world differently than a small wave.
Think about a concrete building.
Yeah, when a radio wave hits a concrete building, the atomic structure of the concrete is so incredibly small compared to the massive size of the wave that the wave essentially just washes right over and through it.
The atoms in the wall can't efficiently absorb a wave that wide.
Which is exactly why I can sit in an enclosed brick room and still stream music on my phone.
Exactly. The macroscopic wave bypasses the microscopic atomic structure.
But as you move down the chart and the wavelengths get smaller, the interactions change dramatically.
Take visible light, for example.
Which is what we see.
Right, and it's measured in nanometers, billionths of a meter.
So tiny.
Because the physical size of a visible light wave is much closer to the size of the atomic structures in that same concrete wall, the atoms in the wall actually absorb and reflect the wave.
It cannot pass through. So the concrete wall is completely transparent to a radio wave, but totally opaque to a visible light wave.
The physical reality of the object doesn't change at all.
Just the dimension of the energy interacting with it does.
Which is a profound realization about the nature of our reality, honestly.
It really makes you think.
It implies that what we consider solid or empty is entirely relative to the wavelength we are using to probe it.
That relativity transitions us beautifully into how the biological world experiences this spectrum.
Because humans are incredibly biased observers.
We really are. We think what we see is everything.
And the slide deck introduces a stunning visual to break that bias.
Focusing on the infrared spectrum.
The slide specifically reads, "Many animals, such as snakes, see in this wavelength of the electromagnetic spectrum."
And the image they provide is so cool. It's a thermal camera shot of an iguana or a lizard.
Against a cool, dark purple background, the lizard is glowing in vibrant, radiant oranges and yellows.
And there's a temperature scale running alongside it. It shows the dark purple at 74.1 degrees and the bright yellow peaking at 100.0 degrees.
Representing the infrared spectrum.
So what does this all mean for us?
Let's do a thought experiment.
Okay. I want you, the listener, to imagine being trapped in a dark room. You turn off all the lights, close the blinds, tape over the cracks in the door.
Total darkness.
To you, the room is pitch black. You are practically blind.
And that's because human optical hardware, our eyes, evolved exclusively to process that one extremely narrow band of tight zigzags in the middle of the chart.
The visible light.
Right. If those specific wavelengths aren't bouncing off objects and entering our pupils, our brains just render the scene as black.
We are functionally cut off from the vast majority of the electromagnetic information flooding the room.
But to a snake in that exact same dark room,
A warm mouse hiding in the corner isn't hidden at all.
not even a little bit. The mouse is emitting infrared waves. It is glowing with its own generated heat.
So to the snake, that mouse is a blinding beacon of orange and yellow light cutting through the dark.
It radically shifts your perspective.
Yeah.
Our human reality isn't the objective truth of the universe.
It's just a heavily filtered simulation limited by the specific organic antennas we have in our skulls.
It's a profound reminder that what we see isn't everything. It's just a tiny sliver of the actual physics happening around us.
We need to unpack the thermodynamic mechanics of what is actually happening there, though. Like, why does the mouse emit infrared in the first place?
It goes right back to the grand theme of energy transformation we discussed at the very start of the deep dive.
The recycling plant.
Exactly. The mouse eats food, metabolizes it, and the resulting kinetic energy causes the atoms within the mouse's body to physically vibrate,
And that atomic vibration, that heat, disturbs the electromagnetic field.
emitting infrared radiation.
So the kinetic energy of the mouse's biology transforms into the electromagnetic energy of an infrared wave.
Exactly. Now, it's important to note that humans interact with this infrared radiation too.
Just not optically.
Right. When you stand near a campfire, the infrared waves emitted by the fire hit the surface of your skin,
And the molecules in my skin absorb that specific wavelength.
which causes them to vibrate faster. And your nervous system translates that localized vibration into the sensation of warmth.
I feel the heat, but I don't see the light.
But the snake has hacked the system.
Through evolutionary adaptation, yes.
Pit vipers possess highly specialized biological transducers called pit organs.
Located between their eyes and nostrils, right?
Yes. These organs contain a suspended membrane that's loaded with temperature-sensitive ion channels.
Okay.
When the infrared radiation from the mouse hits that membrane, it heats up slightly.
Just from the wave hitting it.
Right. This opens the ion channels, triggering an electrical action potential that travels directly to the optic tectum in the snake's brain.
Wow. It translates thermal kinetic energy back into electrical signals, allowing the snake to effectively see the heat.
That is biological engineering at its absolute finest.
It really is. But as incredible as the spectrum is, there is a threshold where it stops being merely informative and starts being actively destructive.
Yes, the curriculum does not shy away from the biological consequences of high-frequency physics.
As we keep moving to the right on the chart, past the visible light and the ultraviolet, the waves become increasingly compressed and frantic.
We're moving into the physical danger of the waves.
The slides pose a very direct, vital question to the student. Which one is dangerous to our cells when absorbed?
And the explicit answer provided is ionizing radiation,
This is perhaps the most critical distinction in the entire presentation.
because it bridges quantum physics directly with human mortality.
The text defines it with absolute surgical precision. It says, ionizing radiation is composed of particles that carry enough kinetic energy to liberate an electron from an atom or molecule.
And it outlines the ultimate fatal consequence. That is, they cause damage to our cells.
The specific waves listed in this danger zone are the extreme ends of ultraviolet, X-rays, and gamma rays.
This raises an important question, though. To fully grasp why this is dangerous, we have to return to your earlier point about the physical size of the wavelength interacting with matter.
Yeah, let's walk through the actual biological timeline of this damage. Because I think liberating an electron sounds a bit too clean and clinical.
It doesn't sound like she caused cancer or radiation sickness.
Exactly. Why does losing one tiny electron actually matter?
Let's use an analogy.
Okay, I want you to imagine your DNA, the tightly coiled molecular blueprints inside the nucleus of your cells.
Picture it as a massive, incredibly complex, delicate Lego castle.
Every single Lego brick is an atom, bound to the next brick by sharing electrons.
A covalent bond.
Right. Now, earlier we talked about radio waves acting like massive, lazy rolling hills.
In this analogy, a radio wave or a Wi-Fi signal is like a giant soft beach ball floating through the room.
It bumps into the Lego castle, but because it is so large and carries so little kinetic energy, it just bounces off or washes around it.
The castle remains perfectly intact.
Non-ionizing radiation just doesn't have the energy to break the bonds.
Exactly. But ionizing radiation like a gamma ray is a completely different beast.
Because its frequency is so insanely high?
Its physical wavelength is incredibly tiny. We are talking about dimensions smaller than a single atom.
So this wave isn't a beach ball.
No, it is a microscopic, hyperdense bowling ball being fired at the speed of light directly into your Lego castle.
Ouch! And because it is so small, it doesn't interact with the macro structure of the castle.
It interacts with a single specific Lego brick.
It hits one specific oxygen or carbon atom in the sugar phosphate backbone of your DNA.
The sheer concentrated kinetic energy of that tiny gamma ray violently impacts the atom and knocks an electron completely out of its orbit,
That is the liberation. The electron is just gone.
which instantly fundamentally changes the chemical nature of that atom. It becomes an ion, a highly reactive free radical.
Because it's missing an electron, it desperately wants to stabilize itself,
So it violently rips an electron away from the neighboring Lego brick.
which breaks the structural bond between the bricks.
The phosphodiester bond snaps. The physical strand of your DNA literally breaks.
And if you have enough of these high-energy waves bombarding the cell, you get multiple double-strand breaks.
The cell's repair mechanisms try to stitch the Lego castle back together. But with so many missing and damaged pieces, it often stitches them together incorrectly.
And that incorrect repair is a mutation.
If that mutation happens in a gene that controls cell division, the cell begins replicating uncontrollably,
That is a tumor. That is cancer.
all stemming from the fact that an invisible wave was mathematically small enough and energetic enough to physically knock one tiny electron off its axis.
It connects the abstract mathematical relationships on the chart directly to human biology and health.
It shows exactly why the dentist places that heavy lead vest over your chest before taking an X-ray.
You need that dense layer of lead atoms to physically intercept and absorb those microscopic bowling balls before they can reach the delicate Lego castles of your internal organs.
Conversely, it explains why you can sit in a house filled with router signals and radio broadcasts all day long without any fear of cellular damage.
The physics simply dictates that those larger waves cannot break your chemical bonds.
It is genuinely astounding how this 2010 presentation manages to weave all of this together.
It really is. I mean, from a set of slides ostensibly designed to keep middle schoolers from shouting out in class, we have basically unspooled the mechanics of the universe.
We've charted the course from the initial philosophical premise that energy is constantly transforming.
Witnessed in the keys of a piano and the grinding of tectonic plates.
We've explored how that energy propagates, not just through the physical collisions of ocean water, but through the self-generating, braided electromagnetic fields.
Just pulling themselves through the cold vacuum of space.
We map the mathematics of that spectrum, proving that the physical dimensions of a wave dictate whether a wall is solid concrete or transparent glass.
We look through the biological hardware of a pit viper to see heat glowing in the dark.
And we trace the violent microscopic physics of a gamma ray shattering a strand of DNA.
And it's worth noting that the slides explicitly direct students to resources from NASA and PBS NOVA to continue this exploration.
Demanding that they adhere to the final classroom rule, never give up on their curiosity.
It is a dense, elegant web of physics, biology, and chemistry.
Truly.
So before we wrap up this deep dive, I want to ask you, the listener, to do something.
Oh, I like this.
Look around the room you're in right now. Just take a look.
Based on the physics we've just meticulously unpacked, recognize that the empty air between you and the wall is a complete illusion.
You are currently sitting completely submerged in a chaotic, invisible ocean of overlapping electromagnetic fields.
There are low-frequency radio waves washing over your building right now.
Microwaves carrying Wi-Fi signals directly through your chest.
Infrared heat radiating off your own skin.
And visible light ricocheting off every single surface at 300,000 kilometers per second just to hit your retinas.
You are the focal point of a massive symphony of invisible energy.
It entirely recontextualizes your immediate environment.
It really does. And, if we want to leave the listener with one final profound implication of these laws, we should return to the speed of light.
Let's do it. We established that these electromagnetic waves travel through the vacuum of space at a constant speed.
The absolute speed limit of the universe.
Yes. Think back to the image the educator used. The glowing spiral galaxy suspended in the blackness of space.
The visible light waves that hit the camera lens to create that photograph, or the waves that hit your eye when you look through a telescope at night?
They did not leave those stars today.
No, because even moving at 300,000 kilometers a second, space is simply too vast.
The chasm is just too wide.
Exactly. The light from a distant galaxy left millions, perhaps billions of years ago.
Those oscillating electric and magnetic fields have been propagating, leapfrogging, pulling themselves forward through the absolute freezing emptiness of the vacuum for eons.
Perfectly preserving the energy of a star that might have died a billion years before the Earth was even formed.
Only now, tonight, does that ancient wave finally collide with the atomic structure of your retina.
Because the journey takes time. Whenever you look up at the night sky, you are physically incapable of seeing the universe as it is right now.
You are, in a very literal sense, looking backward in time.
The night sky is just a massive time machine built out of ancient light.
What a thought to end on. Thank you for joining us on this deep dive into the electromagnetic spectrum. Keep your eyes open, keep analyzing the invisible, and we will catch you on the next one.
Grab a penny out of your pocket or, your bag. Seriously, if you are somewhere where you can get your hands on a physical penny right now, just pull it out and take a really close look at it.
Yeah, really look at it.
Right, because if you think you know what is actually stamped on that little piece of copper, you are almost certainly wrong. Today we're doing a deep dive to show you how a piece of curved glass can turn that completely useless, discarded piece of pocket change into, like, a forensic crime scene.
It's wild.
And in the process of doing that, we're going to completely rewrite how you understand the physical light that is entering your eyes right at this very moment.
It really is a profound shift in perspective. I mean, we walk around every single day assuming that our vision is just this absolute objective truth. We treat our eyes like passive video
Yeah,
cameras.
you open them and the world is just there.
Exactly. You open them, the light hits your retina, and the world is simply there. But the reality is that the visual landscape you are navigating is highly malleable. It can be actively manipulated, bent, stretched, and distorted.
Which is exactly why we are taking you back to the science lab today.
Yeah.
And we have a really fascinating stack of source material for this deep dive.
You do.
On the surface, what we are looking at is a slide deck from a middle or high school science class. It's literally titled Part 1, Lesson 4, Optics Microscopes.
Sounds pretty dry.
Right. But don't let that dry academic title fool you. This isn't just a list of vocabulary words. This slide deck is an absolute masterclass in how to connect abstract physics, classic American poetry, and mundane everyday objects to reveal a universe that is completely invisible to the naked eye.
It is a highly sophisticated piece of pedagogy. The mission of this deep dive is to unpack the exact mechanics of how light is manipulated to reveal those hidden worlds. We're going to dissect the physical anatomy of the tools that make this manipulation possible.
And as I mentioned, we're going to solve a microscopic historical mystery hidden right there on the back of Abraham Lincoln's shoulder. But before we get to the microscopes, before we talk about glass or light or refraction, I want to challenge something right at the top of this lesson plan, because slide 2 of this deck completely threw me off.
Oh, the shield slide.
Yeah, we're supposed to be learning about the thrilling, chaotic discovery of the microscopic universe. But slide 2 features a massive, ancient, battle-worn, circular metal shield.
It's quite an image.
It's covered in rivets, it has a rigid cross pattern in the center, and it just looks incredibly heavy. And right next to this piece of medieval armor is a list of extremely rigid classroom rules.
It is a very stark behavioral foundation, isn't it? The text next to the shield says, make good choices, listen to the teacher and others, please no shout-outs, and one speaker at a time. Please raise your hand.
And then it drops this intense core mantra. It says, first, last, and always. Focus on task completion. Right. It follows that up with directives to avoid distractions, stay organized, help others, and never give up. Okay, I need to push back on this. Starting an optics class with a heavy battle shield and a list of rigid compliance rules feels completely counterintuitive.
How so?
Well, isn't science supposed to be about breaking the rules? I mean, we always picture the eccentric genius with the messy hair, knocking over beakers and discovering penicillin by accident. Why are we locking the students down into this armored, militaristic mindset before they even touch a single lens?
Well, that is the great romantic myth of scientific inquiry, and it's a myth this teacher is actively trying to dismantle right out of the gate. Yes, the outcomes of science, the discoveries are paradigm shifting and wild, but the process of science must be excruciatingly rigid and disciplined.
I guess that makes sense.
The pedagogical framing of that shield is brilliant. Think about what a shield does. It protects you, but it also forces you to hold a line.
So you're saying the shield is a metaphor for the scientific method itself?
Exactly. A science lab is a place of inquiry, but it is fundamentally a place of potential hazard and chaos. You are going to be dealing with fragile glass, highly sensitive precision instruments, and potentially confusing data.
Right. Safety first.
The shield is a subconscious psychological cue to the student. It says, science requires safety and absolute order before discovery can safely happen. If your environment is chaotic, if people are shouting out answers and knocking into tables, you have no idea if the weird result you just observed is because you discovered a new property of light or because the kid next to you bumped your desk.
Or sneezed on the slide.
Right. You have to armor yourself with discipline.
I hear you on the safety aspect, but doesn't a rigid focus on task completion mantra kill the exact kind of creative daydreaming that leads to those breakthroughs? Like, if you are only focused on the task, you might miss the weird anomaly happening in the corner of the petri dish.
It's a valid concern, but consider the cognitive demands of what these students are about to do. They are about to study optics, which involves highly counterintuitive physics.
Yeah, that's true.
The physical discipline demanded by the classroom rules actually mirrors the strict, predictable laws of physics we are about to explore. Light follows very specific mathematical rules. If the students don't follow rules, they cannot accurately measure how the light is behaving. Chaos is the enemy of measurement.
Okay, so we are putting on our armor, we are locking down our behavior, and immediately after that, the lesson forces the students to do a mental warm-up for a review game.
Right.
Again, it has absolutely nothing to do with microscopes yet. It's a math problem. They have to convert 1.25 meters into millimeters, centimeters, and kilometers, and there's this great visual on the slide of a classic battered wooden meter stick.
That mental warm-up is a necessary calibration of the mind. Before you can physically manipulate the microscopic world, you have to prove that your brain can navigate scale.
But why this specific conversion? Why 1.25 meters? That's roughly 4 feet. It just feels so arbitrary.
Well, it isn't arbitrary at all. It forces the student to move the decimal point across multiple orders of magnitude, turning 1.25 meters into 12,250 millimeters or 125 centimeters or 0.00125 kilometers.
Okay, I see.
It's the mathematical equivalent of focusing a microscope lens. You are zooming your conceptual awareness in and out, proving you understand that the universe exists at vastly different resolutions.
Oh, that's a great way to put it.
If you can't grasp that 12,250 millimeters fit inside that wooden stick, you are going to be completely lost when we start talking about the size of a single cell.
So it's basically stretching before the marathon. But the lesson plan also mandates a very specific physical infrastructure for taking notes. The slides explicitly state that students are required to record terms from what they call red slides into their work bundle to be successful.
Yes, and this highlights a critical concept in cognitive science known as cognitive load theory.
I was hoping you would bring that up because work bundle sounds like busy work to me. Why not just tell them to take good notes? Why color code the slides and mandate this specific bundle?
Because when you are learning something as dense and abstract as optical physics, your working memory has a very hard limit. You can only hold so many new variables in your head at one time.
Yeah, I definitely hit that limit in high school physics.
We all do. By explicitly color-coding the essential, non-negotiable information, the red slides, and mandating a dedicated physical space for it, the work bundle, the instructor is pre-sorting the data. They are prioritizing the information for the learner.
Ah, so it acts like an external hard drive for their brain.
Precisely. It creates a structured path through the cognitive noise. The teacher is saying, I know this is overwhelming, so whenever you see a red slide, stop trying to process everything and just physically offload this specific data point into your bundle.
That makes a lot of sense.
Frees up their working memory to actually engage with the difficult concepts rather than panicking about what they need to memorize for the test.
It's the shield again. The work bundle is literally a shield against information overload. I love how deliberate the psychology of this lesson is. But let's actually get into the physics, because this is where the slide deck takes a really surprising, counterintuitive turn.
Yes, the optics.
If I were teaching a class on microscopes, the very first thing I would talk about is making small things look big. Magnification. But this lesson starts with the exact opposite. It introduces a concept called demagnification.
Which is defined on the slide as to make something smaller in appearance.
And the visual evidence they provide to prove this concept is brilliant, but it totally breaks your brain for a second. It's a photograph of a standard optometry eye chart taped to a wall, kind of with the big blocky black numbers that get smaller as you read down.
Right.
There's a massive number 7 at the top left of the chart, but someone is holding a physical magnifying glass between the camera lens and that number 7.
And what happens to the number 7 inside the glass?
It shrinks. Instead of the 7 getting huge and filling up the circular frame of the glass, the lens in the picture is actively shrinking the number compared to the background. The 7 inside the glass is tiny, while the physical 7 painted on the wall behind it is huge.
It's a great visual trick.
Now, as someone who has grown up calling that specific physical object a magnifying glass, this feels like magic. The name of the tool tells you what it is supposed to do. So how is a magnifying glass making something smaller?
Well, this is exactly why the teacher starts here. It immediately challenges the student's baseline assumptions about reality. We assume lenses possess some inherent magical property that just makes things bigger.
Right, because of the name.
Exactly. By showing a magnifying glass actively demagnifying an object, the lesson proves that lenses are actually entirely impartial. They do not care about making things bigger or smaller. They simply manipulate the path of light.
Lenses are impartial manipulators of light. I like that.
The outcome, whether the image appears massive or tiny, depends entirely on the mathematical geometry of the situation. It depends on the curvature of the glass, the distance of the object, and the position of your eye.
Okay, geometry is key here.
The lesson then formally introduces the definition. Lens. A transparent optical device used to converge or diverge transmitted light.
Okay, let's break down those two verbs. Converge, meaning to bring together, to focus light into a single point. and diverge, meaning to spread it apart. And to explain this concept of diverging light, the lesson drops what I think is the most incredible, unexpected cross-disciplinary analogy I have ever seen in a hard science class.
It really is unique.
To explain light spreading apart, the slide shows a beautiful, serene photograph of a dirt road splitting into two separate paths over a grassy hill.
And it isn't just a random picture of a road. The text actively invokes classic American literature. It quotes Robert Frost's famous poem, The Road Not Taken.
It actually forces the students to interact with the poem. It gives them the first few lines, two roads blank in a yellow wood, and sorry I could not travel both.
Ah.
And the students have to physically fill in the blank. They have to know the poem to know that the missing word is diverged.
It is a profound piece of teaching. We are dealing with highly abstract phenomena here. A photon of light is invisible. You cannot hold a light ray in your hand or feel it spread apart. It is entirely conceptual.
Very abstract, yeah.
But every single student intuitively understands the physical, tangible, spatial experience of walking down a path and seeing it split in two different directions.
So they're anchoring the invisible physics in a tangible, emotional visual. But I have to play devil's advocate here. I'm going to challenge this analogy.
Yeah.
Because we use these words casually all the time. We talk about magnifying our problems. We talk about our opinions diverging from our friends' opinions. But physics requires precision. Does the Robert Frost analogy actually hold up scientifically? In the poem, the road splits into exactly two distinct solid paths, path A and path B. But that isn't what light does when it hits a diverging lens, is it? It doesn't just split into two laser beams.
That is an exceptionally sharp critique, and it highlights the inherent danger of using poetry to teach physics. You are entirely correct. The analogy breaks down if you take it literally. The dirt road bifurcates.
Right.
A diverging lens, however, takes a solid bundle of parallel light rays and scatters them continuously in a massive gradient across its entire surface. It is less like a fork in a road and much more like water hitting the back of a spoon and spraying outward in a 360-degree cone.
Exactly. So why use a flawed analogy? Doesn't that risk planting a misconception in their heads that they'll have to unlearn later?
It's a calculated risk by the instructor. You have to remember the goal of this specific slide. The goal isn't to teach the complex wavefront scattering of photons yet. The goal is simply to establish the vocabulary word.
Just getting the concept of diverges down.
To firmly link the word diverge with the conceptual action of spreading apart from a common origin. The Frost analogy is a conceptual bridge. It takes the rigid, straight-line thinking of the student and forces them to realize that light has a trajectory that can be permanently altered. Once they accept that light can be steered down different paths, you can then refine the mechanics of how it scatters.
Okay, so we've established the poetry of light spreading apart and coming together. But how do we actually force a photon to change its path? Because a piece of glass just looks like a solid flat barrier. This brings us to the actual geometry of light.
Yes, back to the straight edges.
Exactly. The lesson moves away from Robert Frost and goes straight back to the rigid discipline of the shield.
Yeah.
It literally demands that students use a straight edge for the next activity.
You cannot draw optical ray diagrams freehand. If your line is off by a single degree, the entire optical system fails. You must use a ruler. You must be precise.
The source material provides explicit, step-by-step, mechanical drawing instructions for the two main categories of lenses. Let's start with the converging lens. The slide illustrates this as a double convex lens.
Right?
Visually, it is drawn so that it's much thicker in the middle and it tapers off to sharp points at the top and bottom. It looks exactly like an American football standing perfectly on its end, or maybe a symmetrical almond.
And how does the diagram illustrate the behavior of the light interacting with this football shape?
It shows these perfectly parallel red lines representing light rays, entering the blue-tinted lens from the left side. As soon as those red rays hit the curved glass, they all violently bend inward. They angle toward each other, funneling down until they all perfectly intersect at a single distinct black dot on the far right side of the diagram. And the dot is labeled with a capital F.
That capital F stands for the focal point. This diagram is the foundational blueprint for all optical engineering. But we need to explain why this happens. Why doesn't the light just pass straight through the clear glass?
Yes, please explain the mechanism because the slides show the what, but I want to understand the how.
Well, the mechanism is a phenomenon called refraction. Think of a light ray not as a tiny bullet, but as a wide wave, like a wave rolling in from the ocean toward the beach.
Okay, a wave.
Light travels at an absolute speed limit in a vacuum, but when it passes from a less dense medium like the air in the classroom into a denser medium like the solid glass of the lens, The physical density of the glass actually forces the light wave to slow down.
So the glass is acting like mud slowing down a car tire.
That is actually a perfect mechanical analogy. Imagine you are driving a car on smooth asphalt and the right side of the road turns into thick mud. Your right tires hit the mud and slow down instantly, but your left tires are still on the smooth asphalt moving fast. What happens to the car?
The car is going to violently swerve to the right toward the mud. It pivots.
Exactly. The car pivots. Because the double convex lens is curved, the top and bottom edges of the incoming light wave hit the sloping glass at an angle. The part of the wave that hits the glass first slows down first, causing the entire trajectory of the wave to pivot inward.
Oh, that makes so much sense.
Because the glass is thickest in the middle and curved symmetrically on both sides, it acts as a geometric funnel. It steers every single one of those parallel rays to pivot by the exact mathematical amount required to make them all crash into each other at that single focal point.
So a convex lens is essentially a funnel for visual data, gathering all this diffuse light into a single, intensely concentrated point. That makes sense. But then the lesson introduces the exact opposite, the diverging lens.
The double concave lens.
Right. This is illustrated as a double concave lens.
Mm.
And physically, it is the inverse of the football. It is thin in the middle, incredibly thick and wide at the top and bottom. It curves inward on both sides. It looks like an hourglass.
And following the logic of your car in the mud analogy, the behavior of the light is completely inverted.
Right, because the slope of the glass is facing the other way. The parallel red rays hit this hourglass shape, and instead of funneling together, they splay outward. They fan away from each other as they exit the right side of the glass.
Yes.
But here's where the diagram gets incredibly strange.
Yeah.
It draws these dotted red lines backwards. It traces the trajectory of the spreading rays backward through the glass lens all the way to a point on the left side of the diagram, the front of the lens. And it labels that point with an F as well.
That specific detail is arguably the most complex concept in this entire lesson. That F on the left side is what physicists call a virtual focal point.
Virtual. So it isn't real. But the line is drawn right there on the paper.
The point exists mathematically, but the physical light rays do not actually exist there. The real photons are traveling forward and spreading apart into the room. But think about what happens when your eye receives those spreading rays. Your brain evolved to assume that light always travels in a perfectly straight line. So when your eye catches those diverging rays, your brain automatically traces them backward in a straight line to figure out where they came from.
Oh, wow. So your brain projects a false origin point behind the lens.
Precisely. Your brain perceives the light as originating from that single virtual point hovering in empty space. It is a biological optical illusion facilitated by the geometry of the glass.
That is wild.
And this, connecting back to the beginning of the lesson, is exactly why the number 7 on the eye chart looked smaller when viewed through that specific lens. The diverging lens spreads the light out, forcing your brain to trace the rays back to a virtual focal point that produces a smaller, closer image of the 7.
That is absolutely mind-bending. We aren't just manipulating light, we are actively hacking the brain's visual processing software. And apparently, just using a football shape and an hourglass shape isn't enough, because the lesson then expands into a massive taxonomy of lens profiles.
It does.
It doesn't just show 2 lenses, it lists 6 distinct shapes side by side.
Yes, the engineering complexity scales up dramatically here. We have the biconvex and biconcave, which we just discussed. But then the slide introduces the planoconvex, meaning one side of the glass is perfectly flat, like a window pane, and the other side bows outward. And the planoconcave, one flat side, one bowing inward.
And then it introduces these beautifully named meniscus lenses. Positive meniscus and negative meniscus. Visually, they look like crescent moons. They curve in the exact same direction, sweeping across the diagram, but one is slightly thicker in the middle and one is slightly thicker on the outer edges.
Very elegant shapes.
Now, let me challenge this taxonomy.
Okay.
Why on earth do we need 6 different highly specific shapes just to execute 2 basic functions, bringing light together or spreading it apart? It feels overly complicated.
It feels complicated because nature is imperfect, and these 6 shapes are the vocabulary engineers use to correct those imperfections. A simple biconvex lens, the football shape, can focus light, but it does a sloppy job of it.
Really? How so?
Because of the spherical nature of the curve, the light rays hitting the very outer edges of the lens bend slightly more than the rays hitting near the center.
So they don't all meet at the exact same focal point.
Correct. They miss the target slightly. This creates a blurry, distorted image. In physics, this is called spherical aberration. If you look through a cheap magnifying glass, you'll see the edges of the image look warped and rainbow-colored.
Oh, I've definitely seen that.
To fix this, optical engineers have to combine different lens shapes. They might glue a biconvex lens to a negative meniscus lens. The specific curve of the meniscus lens is mathematically designed to cancel out the optical errors of the biconvex lens.
So it's like noise-canceling headphones, but for light. One lens creates an error, and the next lens creates the exact opposite error, so the light waves perfectly align.
That is a phenomenal analogy. Yes, it is optical noise cancellation. It's like tuning a piano. One string gets you a note, but multiple strings tuned together in harmony give you a perfect chord. And the students actually have to prove they understand this harmony in the physical world.
Right, the Raybox activity.
Exactly. The slides detail a real-world demonstration using a piece of equipment called a Raybox.
I looked at the image for this activity, and it looks like something out of a sci-fi movie. There is a small black device sitting on a table, and it is emitting four distinct, perfectly parallel, bright red laser lines right across the surface of the desk.
The Raybox is a vital teaching tool because it makes the invisible geometry we've been drawing actually visible in three-dimensional space. The instructions for the activity are essentially a puzzle.
How does it work?
The students at their lab tables are required to use both a convex lens and a concave lens together to focus that beam of four lasers exactly onto a single specific dot taped to the table.
It is literally a bank heist movie where the cat burglar has to use mirrors and glass to redirect the security lasers.
I love the tactile nature of this. They can't just slap a convex lens down and be done with it.
No, they can't. They have to physically realize that the convex lens will bring the lasers together, but maybe it brings them together too sharply, missing the dot. So they have to introduce the concave lens to spread the beams back out just a fraction of an inch to hit the target perfectly.
They are actively steering light. They are taking the abstract geometry from their straight-edge drawings and applying it physically. And this precise physical control stacking combinations of differently shaped glass to steer photons with microscopic accuracy is exactly what allows us to build the massive optical machines used in professional laboratories.
Which is the perfect transition into the actual hardware. We have mastered the math, we have played with the lasers, and now we are finally getting our hands on the microscopes.
Finally.
But true to the strict, shield-like discipline of this teacher, we don't just get to look through the eyepiece. The slides present a massive warning label. Warning, three-part question.
The cognitive load is increasing significantly, so the architectural structure of the rules has to hold the students in place.
The slide shows photographs of four different magnification devices. And the students are hit with this rigorous three-part interrogation for each one. They must identify the device by name, they must describe the specific type of specimen it is meant to magnify, and they must describe the specific types of internal lenses required to make it work.
A very thorough breakdown.
Let's look at this progression because it ranges from the beautifully simple to the staggeringly complex. Device number one is just a basic handheld magnifying glass with a black plastic handle.
Which, based on our taxonomy, we now know contains a convex lens. And its application is meant for large, opaque specimens. You use it to look at the texture of a rock, or the text on a document, or an insect.
Device number two is the classic heavy metal workhorse of every high school science lab, the compound light microscope.
The standard.
Device number three is something called a stereoscope, which looks a bit like a microscope, but it has double eyepieces sticking out of the top, almost like a pair of binoculars grafted onto a stand. And then, device number four.
Yes, number 4.
The fourth image looks like a piece of a NASA command center. It is a massive, multi-part desk console covered in screens and dials, completely dwarfing the person sitting next to it. It's an electron microscope.
The progression of these 4 images tells the evolutionary story of our ability to see. But before we get to the extremes, the lesson demands that the students rigorously dissect the anatomy of the compound light microscope. There is a highly detailed diagram of the device that the students must label using a provided word bank.
Let's walk through that anatomy because it actually applies everything we just learned about steering light and managing chaos. You've got the physical frame, the base at the bottom, and the arm curving up the back. These are heavy metal components.
Right, for stability.
Then you have the optical pathway. The light source is built into the base, shining directly upward. Above that is the stage, which is the flat platform where you put your glass slide held in place by stage clips. And hovering directly above the stage is the body tube, which holds the lenses.
Let's focus on those lenses because the diagram highlights the revolving nosepiece at the bottom of the body tube and the eyepiece at the top. The revolving nose piece is the mechanical realization of the lens taxonomy we discussed earlier.
Oh, because it holds different lenses.
Exactly. It is a rotating disc that holds multiple objective lenses, usually 3 or 4 metal cylinders of different lengths. Inside each of those tiny cylinders is a specific, custom engineered combination of those convex and meniscus glass shapes. By rotating the nose piece, you can instantly swap out one complex optical equation for another, dialing in the exact magnification power you need.
And the term compound light microscope is key here, right? It isn't just one lens doing the work.
Exactly. It compounds the physics. The objective lens hovering right over the specimen captures the light and magnifies the image. That magnified image is then projected straight up the hollow body tube where it hits the eyepiece lens.
Okay, I follow.
The eyepiece then magnifies that already magnified image a second time before it hits your eye. It is an exponential multiplication of optical power.
Stacking the lenses to multiply the effect. But there are three other parts on this diagram that I find deeply fascinating because they aren't about magnification at all. They are entirely about control and restraint. First, there's a component called the diaphragm, located right underneath the stage, between the light source and the specimen.
The diaphragm is an absolute stroke of engineering genius, and it requires a deep understanding of contrast. It is essentially an adjustable mechanical iris, very much like the pupil in your own eye or the aperture ring in a professional camera lens. Its sole function is to control the absolute volume of light that is allowed to hit the specimen.
But wait, if you're looking at something microscopically small, wouldn't you want as much light as possible? Wouldn't you want to blast it with a spotlight so you can see every detail?
That is the intuitive assumption, but it is optically incorrect. If your specimen is very thin and highly transparent, like a single layer of onion skin or a translucent amoeba, blasting it with maximum light will simply wash the image out entirely.
Oh, because it's transparent.
Right. The intense light waves will flood the lens and destroy the delicate shadows and boundaries of the cells. You won't see anything but a blinding white glare. To actually see the transparent structures, you have to close the diaphragm down. You restrict the light to a narrow beam, which increases the physical contrast and allows the subtle details to cast microscopic shadows.
So it's about contrast, not brightness.
Exactly. It reminds the user that more power doesn't always equal a better image. Control is more important than raw output.
That perfectly explains the next two parts on the diagram: the coarse adjustment knob and the fine adjustment knob. These are the dials on the side of the arm. When you turn the coarse knob, you can physically see the stage moving rapidly up and down. But when you turn the fine knob, the stage barely seems to move at all. Why do we need two different gears for the same action?
To answer that, we have to go back to the geometry drawings we did with our straight edges. Remember that single precise black dot labeled F, the focal point?
Right, where all the red lasers crashed into each other?
That focal point isn't a vague area. It is an infinitesimally small, mathematically fixed coordinate in three-dimensional space. The objective lens cannot change its focal point. Therefore, to see the specimen clearly, you must mechanically move the specimen until it rests exactly within that invisible microscopic plane of focus.
Ah, so you move the stage to meet the focal point.
Yes. The coarse adjustment knob is a macro tool. It gets you into the general neighborhood. But if you use it while looking through high magnification, you will blow right past the focal point, or worse, you will drive the glass slide right up into the glass lens and shatter them both.
Which is a classic, terrifying, middle school science lab mistake. I can hear the crunching glass in my head right now.
We all can, exactly. The fine adjustment knob is geared so low that turning it heavily only moves the stage a fraction of a millimeter. It allows you to hunt for that perfect optical coordinate without destroying the equipment. A fraction of a millimeter makes the difference between seeing the rigid structure of a cell wall and staring into a blurry, indistinct gray fog.
Which perfectly explains why the assignment immediately follows up the diagram with two behavioral lab questions. How do you carry a microscope in the lab? And what are three things you should do when putting the microscope away? The answers usually involve holding it firmly by the arm and the base, turning the light off, carefully wrapping the cord, and rotating the nose piece back to the lowest, shortest power objective so it doesn't scratch the stage.
We return to the shield, the discipline. You are handling a precision instrument that relies on perfectly aligned, highly engineered glass shapes interacting with light at microscopic tolerances.
Yeah, you can't be careless.
If you swing it around the room with one hand like a toy, you will jar the lenses out of alignment. The focal points will shift permanently, and the machine becomes a useless piece of metal. Order and discipline maintain the optics.
Okay, so we have this incredible discipline mastery over light using glass lenses and mechanical diaphragms, but I have to go back to that fourth image on the slide, the electron microscope.
It's a leap, isn't it?
We go from a magnifying glass to a compound microscope, and then we leap to a machine that takes up half a room. If a regular microscope uses visible light, what on earth is an electron microscope using? And let me ask the naive question, why can't we just take the compound microscope concept, build a really, really long metal tube, and stack 100 glass convex lenses inside it to magnify the image down to the size of a single atom?
That is not a naive question at all. Actually, it is the exact question that drove 20th century physics. It raises a profound point about the fundamental, hard limits of nature.
What limits?
The prompt implies this limit by presenting the electron microscope as an entirely different category of device separated from the glass lenses. The reason you cannot just stack 100 glass lenses together to see an atom has nothing to do with the quality of the glass. It has to do with the physical nature of light itself.
What do you mean? Light is just what lets us see.
Visible light does not travel as a perfectly straight, infinitely thin laser beam. It travels in a wave. And those waves have a specific, measurable physical size, a wavelength. The distance from the crest of one light wave to the crest of the next is roughly 400 to 700 nanometers.
Okay, so a wave has a physical size.
Now, an atom or a virus is significantly smaller than 400 nanometers.
Okay, so the thing we were trying to look at is physically smaller than the tool we are using to look at it.
Precisely. You cannot use a wave to clearly image something that is smaller than the wave itself. It is a concept called the diffraction limit.
The diffraction limit, let's break that down.
Think of a massive ocean swell, a huge wave rolling toward a pier. If that massive wave hits a single, thin, wooden piling holding up the pier, the wave doesn't bounce off and create a perfect image of the piling. The wave is so big that it just wraps right around the word and keeps going. It ignores it.
Wow. So if we shine visible light at a virus, the light wave literally washes over the virus without interacting with it in a way that our lenses can capture. The virus is too small to cast a shadow in the light wave.
Exactly. Stacking more glass lenses won't help because you are just magnifying a blur. The tool is simply too blunt. So while the deep mechanics are beyond the strict optics of our middle school lesson plan, the name electron microscope tells us the brilliant solution scientists engineered.
Using electrons instead of light.
Yes. Instead of bending waves of visible light using curved glass, they fire a beam of electrons at the specimen. According to quantum mechanics, electrons also travel in waves, but their wavelength is thousands of times smaller than a photon of visible light. The electron wave is small enough to actually bounce off the virus.
That is amazing.
And because electrons have a negative charge, scientists use powerful electromagnetic fields instead of physical glass to steer and focus the beam. It is a completely different quantum paradigm of seeing.
That is absolutely mind-bending. We hit the physical limit of the universe's lighting system, so we just invented a new one using subatomic particles. But what's brilliant about this lesson plan is that it doesn't dwell on the unimaginably small.
No, it brings it right back.
It actually steers us away from the quantum realm and brings us firmly back to something we can hold in our physical hands. It transitions to what I am calling the micro-mystery of the modern penny. And to solve this mystery, we have to use the third device on that list, the stereoscope.
The slides provide a highly evocative, almost whimsical note for the stereoscope. It tells the students that this device lets you see the image in 3D, quote, like a bumblebee.
I cannot overstate how much I love the bumblebee analogy, because we just spent all this time dissecting the compound microscope, and we learned that to use it, you have to take a 3D object, like a drop of pond water, squish it completely flat under a glass slip, and shine light directly through it from the bottom. You are destroying the three-dimensional nature of the object to see its internal structure.
Right, you lose the depth.
But the stereoscope is entirely different. It has two separate eyepieces sticking out.
It relies on stereoscopic vision, which is exactly how human depth perception works. By providing two completely separate optical pathways through the device, one dedicated solely to your left eye and one dedicated solely to your right eye, the lenses capture the object from two slightly different angles.
Just like our eyes.
Exactly. Your brain then receives those two separate feeds and mathematically combines them to perceive deep texture, shadows, and topography. And crucially, you do not shine light through the specimen, you use lamps to shine light down onto the surface of it. The stereoscope is specifically engineered for solid, opaque objects that you cannot flatten.
Objects exactly like a penny. The specific activity in the slides instructs the students to put a common pocket penny under the stereoscope and adjust the lighting. Now, I want you to really think about the psychology of this for a moment. A penny is arguably the most mundane, ignored, practically useless object in our daily lives.
People literally throw them on the ground.
Or leave them in take-a-penny trays. But this teacher is instructing the students to place this discarded piece of copper under a highly engineered optical instrument, turning it into a vast landscape of hidden microscopic data.
The instructions are very specific. They tell the students to look for a single, tiny, microscopic letter stamped just below the year on the coin. It is a profound lesson in the power of observation.
What are they looking for?
The slide explains that if they adjust their focus and find a tiny D, it proves the coin was minted in Denver, Colorado. If they find an S, it came from the mint in San Francisco. And the slides note a fascinating piece of historical trivia here. If you find an S, it means you are holding an older penny, because the San Francisco Mint no longer produces coins for general public circulation.
That's pretty
If
good.
there is no letter there at all, it was minted in Philadelphia.
So in the span of one activity, the students are transformed from frustrated physics learners into forensic historians. They are using the optical properties of convex lenses to trace the geographical origin of a piece of metal they found in their couch cushions.
It's a great application.
But the mystery actually goes much deeper than just the mint location. The slides reveal a hidden piece of American history. It states that in 1918, the initials VDB were added to the penny. And then, it hits the students with a multiple-choice question. Who was the engraver of the modern penny?
The options provided on the slide are A. Arnold Smith Jr., B. Victor David Brenner, C. Simon Ohms Pierce, D. Madeline Jana Corbel Albright, or E. There are no initials.
Okay, this is basically a logic puzzle thinly disguised as a history question. If the students actually found the microscopic initials VDB using their stereoscope, then the obvious logical answer has to be B, Victor David Brenner. Have you ever looked at the change in your pocket closely enough to find a man's secret initials hidden on Abraham Lincoln's shoulder? I certainly haven't.
Very few people have. And what is truly beautiful about this specific activity is the subtle pedagogical trick being played on the students. Think about what they're actually doing.
Playing a game.
Sort of. The teacher is tricking them into practicing complex refraction physics. They are actively adjusting mechanical fine focus knobs, manipulating the diaphragm to get the shadows just right, and managing the intense cognitive load of operating a new piece of hardware.
But they don't know they're doing it.
Exactly. They don't feel like they are doing tedious physics drills. They feel like they are on a scavenger hunt for a secret century-old code. The tool itself, the complicated stereoscope, recedes into the background of their mind, and the pure thrill of discovery takes over.
It perfectly, elegantly ties back to the very first slide of the day. You put on the heavy armor of the shield, you follow the strict rules of the lab, you memorize the abstract math of how the glass bends the light, and your ultimate reward for all that discipline is that you get to uncover secret histories hidden in plain sight. You earn the right to see the invisible.
It completely transforms the mundane into the miraculous. It teaches them that boredom is simply a failure of observation. If a penny is boring, you just don't have the right lens.
I think that is the perfect summation of this entire lesson plan. If you are bored, you just don't have the right lens. Let's briefly look back at the immense journey we've taken through these slides today. We started in a highly structured, almost intimidating environment, armed with a metaphorical battle shield of rules and the mental calibration of converting meters to millimeters.
A lot of ground covered.
We analyzed how a Robert Frost poem about diverging dirt paths in a yellow wood perfectly captures the physics of a concave lens scattering light. We painstakingly dissected the intricate, precision-engineered machinery of a compound microscope, learning how to use coarse and fine adjustments to hunt down an infinitesimally small mathematical focal point. And we ended up using 3D bumblebee vision through a stereoscope to become forensic historians, hunting for Victor David Brenner's hidden initials on an everyday penny.
It is a phenomenal, deeply considered progression from the highly abstract mathematics of refraction to the incredibly concrete, tactile reality of holding history in your hand.
But, as is always the case when we look closely at something, there's always a deeper layer to explore. I want to leave you with a final, provocative thought derived from the very last piece of this source material.
Oh, the link at the end.
Yes, on the final slide, there was a small link provided for students who want to go further. It directs them to a website called microbeehunter.com, and it encourages them to research something called wet mount slides and a technique known as oil immersion.
Ah, oil immersion. That is a truly fascinating high-level optical technique that pushes the physical limits of glass lenses.
Right. We just spent this entire deep dive talking about how light bends, how it refracts, when it moves from the thin air of the classroom into the dense curved glass of the lens, and then back out into the air. That change in density is the only thing that allows lenses to work, but oil immersion throws that entire concept out the window.
It does.
It involves taking a literal drop of specialized, highly transparent oil and dropping it directly onto the glass slide covering your specimen. And then you lower the objective lens of the microscope until the glass physically dips into and touches the oil. You create a continuous, unbroken liquid bridge between the specimen and the lens.
And the physics of why you do that are brilliant. That specific oil has the exact same refractive index as the glass. It shares the same optical density. By creating that liquid bridge, you completely eliminate the air gap between the slide and the lens.
So the light doesn't bend at all when it leaves the specimen.
Exactly. Without the air gap, the light doesn't scatter or bend as it leaves the glass slide. It travels straight through the oil directly into the lens, capturing every single photon. It allows for incredibly high, ultra-crisp magnification, up to 1000x power, without losing the resolution to scattering light.
So I want you to ponder that as you go about your day. If just manipulating pieces of solid, curved glass and empty air can reveal a secret code hidden on a penny in your pocket, what entirely new universes, what terrifying or beautiful biological structures might be revealed when we start bending light through continuous bridges of liquid? We look around our world, assuming our vision is absolute and that we see everything there is to see. But the truth is, the world is saturated with invisible data, just waiting for the right lens or the right drop of oil to bring its secrets into focus.
It's a powerful reminder that there is always, always more to see if we are willing to put in the disciplined work to adjust our perspective.
Exactly. So the next time you think you see the whole picture, the next time you think you understand a situation completely, remember that your internal optics might just be out of alignment. You are staring into the muddy waters of a physical reality that can be bent, magnified, and completely shifted by the tools you use to view it. The world isn't just what you passively see. The world is what you actively, deliberately choose to look for.